So we're getting a lot of support. And with that, I want to end my presentation, but I did want to leave you with the thought that this is a highly capable, underpublicized cybersecurity school, and we're about to take care of the underpublicized part. And I think you'll be hearing a lot more about us, particularly when we make the formal announcement about the scholarship. But if you are a student in this room and that scholarship is attractive to you and you've got a good GPA, if you're an undergraduate that's graduating and maybe you'd like to go on for a master's, or if you're a master's student and you got a couple of years left, come and see us and let's talk about cyber studies and how this program might be able to help you. Okay, Tommy, if you want to come on up here and get your computer. What's that?
Do you have time for questions?
I could take a couple of questions and then I'll introduce Tommy.
If you have any questions, you can speak loudly while we get the microphone.
Yes, sir.
You mentioned PhD. Is there a plan for a PhD program in cybersecurity?
Right now, we have emphasis areas. You know, PhD is a research program, so you can be in business or engineering or computer science, but the focus of your research would be in cybersecurity. I'm really not personally a believer in creating a degree for cybersecurity. It seems like some schools have done that. But that's almost like creating a degree for the problem du jour. You know, we'll have degrees in homeland security. There are some of those. I mean, the next thing we'll have is degrees in whatever problem occurs next week. I think the important thing is to take the fundamental discipline and get people to research that specific area that's of interest to them. When I did my cybersecurity PhD, I did it at Kansas State University in computer science back in the 80s. But you know, it still was cybersecurity, it's just called computer science. But I focused in that area. So I guess the short answer is we're not planning a cybersecurity PhD, but we certainly have an emphasis area track in that area. Other questions? Wow. Yes, sir, yellow shirt, way in the back.
Yeah, I got a question for you. You mentioned you're building a SCADA lab. You guys are in the university planning on interfacing with the Department of Energy or TVA?
If interfacing means seeking grant funding from them, absolutely. You know, you have to kind of define interfacing. If interfacing means sharing our results with them, certainly. That's to our advantage to do that. When Tommy talks about the SCADA work that we did at Mississippi State, he is working some with Department of Energy or Department of Energy labs, plus he also does a lot of work with utilities. His particular area has been Pacific Gas and Electric out on the West Coast. TVA has been a little tougher to get into. One of the dilemmas in SCADA security is that most SCADA vendors aren't really interested in having you come in and show them where their vulnerabilities are. Not quite sure why, but it's been real hard to get in. Huntsville Utilities, on the other hand, has been pretty open. We would hope to do more work with them. Any other questions?
One more, President.
Yes, sir.
You mentioned community colleges. Would a community college student be eligible for the scholarship you mentioned earlier?
We hope that they will apply, absolutely. Which community college are you with?
Sneed said.
Sneed? Yeah, in fact, I met with some of the folks from Sneed the other day. I'll be sending an announcement, an application process out to Sneed and to Northeast Alabama and to Calhoun for sure, and I think Drake too. Drake's in this area. So those are the ones I know about that I want to get applicants from.
Thanks, sir.
Yeah, absolutely. All right, so I've got a bio here that I'm absolutely not going to read on Tommy. I'm just going to tell you what I know about him. First of all, he's a lot younger than he really is. He's a lot older than he really is what I should say. He looks younger. But Tommy spent a large number of years, almost 20 years, with Texas Instruments in Texas, and then decided to go get a PhD at Southern Methodist University and focused in cybersecurity under a friend of mine that I know. And he came to Mississippi State some years ago, gave a wonderful lecture on his research ideas, and then we got him hooked into SCADA security. He has a habit of attracting some of the best students that I've ever seen, and in fact one of his demos today was actually built by one of his undergraduate students who later went on for a PhD, but the guy built it as an undergraduate. Of course, he was a National Merit Scholarship finalist, but still, he was an undergraduate. And he's had a number of grants and is doing active work in SCADA security around the country. His sponsors include the Army, it includes Pacific Gas Electric, the National Science Foundation, and many, many others. So I don't want to take a lot of his time away. I'd just tell you that you're in for a treat. This is a really interesting area to look at. And before he gets into it, let me just remind you that your daily lives depend on critical infrastructure, SCADA systems, your water into your homes, your sewer system, your power. Almost anything that you take for granted that works properly can be attacked, in some cases quite easily, by intruding on these SCADA systems. And so for the last several years, we've been engaged in just looking at what some of those vulnerabilities are. So with that, I'm going to leave it to Tommy to tell you more about that area. Tommy? I'm supposed to give you this. You got it?
Yeah.
There's the clicker.
Okay, thank you. My name is Tommy Morris. I'm from Mississippi State University. I'm currently an assistant professor in electrical and computer engineering, and I have a couple of research center roles as well. I'm director of a center called the Critical Infrastructure Protection Center, and also associate director of a new center called the Distributed Analytics and Security Institute. And I'll tell you what those are as I go through the talk, if I can get my slides to go. Okay. So before I start in on the SCADA security, I just want to talk about where I come from. I'll talk about my two centers, and then we'll kind of go into the cybersecurity for critical infrastructure. So the first center is the Critical Infrastructure Protection Center, and I start here. Ray mentioned critical infrastructure is very important to all of our lives. The Department of Homeland Security has actually defined 18 critical infrastructure areas that cover a lot of different facets of our economy and our government, that if any one of those goes under for whatever reason, they will have an immediate impact on our economy or the safety of the citizenry. So a couple of the critical infrastructure that I concentrate on are up at the top of this slide. We've got a dam there that's probably also, that one is an electric generator as well. There's a water tower next to it. There's a pipeline next to that, and then electric transmission. So I concentrate in those areas. The Critical Infrastructure Protection Center looks at identifying vulnerabilities in these types of systems, and then looks at ways to actually close those vulnerabilities. And finally, we train engineers and scientists so the folks here in the audience can actually, or some of you can hire them and put them to work. Our new center is called the Distributed Analytics and Security Institute. This one, we're partnered with Pacific Northwest National Laboratory, and we'll be researching at the intersection of big data analytics, high performance computing, and cybersecurity. So that one is going to kick off with a grant from a DoD agency in hopefully May. We're still actually working on actually getting the check cut. Now we'll move in. What I'm going to do in this talk is actually give an overview of my research. I've been at Mississippi State for 6 years, and I'm going to talk through, I do a lot of projects. I couldn't squeeze it all into 30 minutes actually, which was actually interesting to me. It's nice to do that kind of audit of yourself and see what all you've done in 6 years. But I squeezed as much of it as I can into the slides, and so at some point Ray will come back up with a hook and pull me off. But so I'm going to start with what is actually ICS security. I do ICS security almost primarily for power systems and SCADA. We'll talk about intrusion detection systems, cyber test beds and attacks, and then cybersecurity, some work I did hardening some devices for Pacific Gas and Electric, and then finally a little bit of what I'm doing for cybersecurity education. We have a lot of research partners, and I just wanted to show these off real quick. I mean, I've worked with a lot of different people in 6 years. I have projects with NSF, Department of Homeland Security. I'm really proud of the fact that I've worked directly for Entergy, which is an electric utility that covers 4 states here in the Southeast, and Pacific Gas and Electric, which is Northern California, one of the largest electric utilities in the world, and then all of these other partners. I want to start with our labs. Ray mentioned some of the labs that are going to be coming here to UAH, and I think that some of them are going to be similar to this SCADA lab. But what attracted me to MSU and what might attract you to UAH when these labs are available was this very lab, and actually Ray as well. But what we have is a set of what I call laboratory scale SCADA systems. They are fully functional SCADA control systems that have commercial programmable logic controllers, which is a mini computer that actually connects to a physical process and monitors and controls that process. We also have commercial software that's called human-machine interface. The bottom row is actually human-machine interface screen captures, where operators will sit at a screen and monitor a system and actually provide control as needed. So we actually have 7 of these labs in our SCADA security lab. I only put 4 on the slide, but they're all tabletop. They're all fully functional. So like the water tower on the left holds a liter of water. That liter of water drains down into a pool, and then a pump pumps water back up just like a real water tower, and then the PLC monitors the level of the water in that tower and turns the pump on and off as usage changes. We have a gas pipeline. The next one over is a factory automation simulation. It sorts those pucks, sends them left and right based on color, and the next one's actually modeling a oil storage tank, but ours holds water. And one of the reasons I want to show this lab, and I'll show you my other lab real quick. Oh, actually, I won't. One of the reasons I want to show you this lab is because it was very expensive. Over a few years, we developed a lab. It was probably $200,000 to $300,000 total. So we're very lucky at MSU to have this lab. And what it allows the students to do is go in, and myself as well, to go in and develop attacks and actually test intrusion detection systems and other architectures and or research outcomes to ensure or check if validate our hypotheses. A lot of universities don't have that because it's so expensive. And so what I'm going to show you in a minute is actually a virtualization of this lab. I have a demo I want to show. But a lot of universities do have, they do something like what I did on this slide. We developed in that lab, I had a PhD student, he created 28 total attacks in a couple of different categories. Reconnaissance, which is basically trying to find a victim. That's the first thing attackers do, is try to find a machine and fingerprint it, and then they will move on to a larger scale attack. And then the next 2 are response injection and command injection. Those are basically sending commands or changing measurements so that an operator loses control of his system. And then finally, denial of service is just breaking a communication link. But what we did is we developed 28 attacks in these 4 broad categories, and then we followed that up with some intrusion detection system research. And so this is a detail on one of the attacks. The undergraduate student that was the National Merit Scholar did this as a junior at Mississippi State. We had these labs. The labs actually communicate from a master to a slave via wireless radio. We bought online an extra wireless radio and had the student look, could you actually find a victim radio using a radio you bought offline. So that was discovery, and he very quickly found that within 24 hours with a brute force attack, he could find a victim. Then after he did that, I asked him, okay, well, let's break in to our victim. And so he found it takes a while, but with a brute force attack, you could break into that wireless link in less than 30 days. And you have to remember 30 days might sound long if you're talking about Wi-Fi at Starbucks, but 30 days when you're talking about a fixed placement of a gas pipeline or a water treatment system is not that bad. You can set up a Yagi antenna pointed at that facility from another location and take your time. And then after we got into the system, we looked at what can we do. The first thing we did was a denial of service attack, and that's shown on this picture. Hopefully you can see it. Turns out that the radios don't do a very good job of arbitrating the communication. And so when we started the attack, it's very, very simple. We had one radio that infiltrated the system start sending random numbers continuously. And that caused the other slave in the system, the valid slave, he's actually listening to the link, and he listens for the line to be dead before he'll transmit. So if we continuously transmit, he can't. And so what that does is break the communication link and stops the operator from being able to monitor the system. And so what's shown on the screen is a screen capture where it says 17.9 psi. That's what an operator would be seeing, while we had the system in manual mode, pumping, and it pumped up to 55 psi. That would be very dangerous in real life. You would most likely burst your pipe and hurt people. I already mentioned, so we have a unique lab. A lot of people around the world, there's 10 or 20 labs. I don't think any of them are as good as what we have at Mississippi State, but a lot of people have inherited equipment over time, and they build up a small SCADA lab, and then they start developing their own attacks. And in my research area, intrusion detection, which intrusion detection, by the way, is detecting if somebody has broken into your network or is attacking you. What researchers, including us at Mississippi State, is we'll develop our own attacks, and then we will develop an IDS that it's impossible not to bias it toward your attacks when you have the attack sitting right there. And then we'll use our attacks to validate our IDS, and then we'll go off and publish how great our IDS is. And that causes a couple of problems. One is, I had a friend who he doesn't know it. We review each other's journal articles, but we do it in secret. And I reviewed a friend's journal article once, and he insisted on writing that his IDS was 100% accurate, and I just couldn't accept that. But without breaking the anonymity, I couldn't call him up on the phone, so it was this back and forth. I reviewed the paper, said absolutely cannot have a statement 100% accurate. And he wrote back, but it is 100% accurate on my system. And so, through this 4-month back and forth, all I could get him to do, if I was going to let his paper be published in a timely manner, was write that it was 100% accurate for the data set that he had. He refused, and back and forth over a 4-month length there. It was hard, but he refused to do any more than that. And that really made me mad. Honestly, it did. And so now, I want to prove that it's not 100%. I want to prove mine's better, but I can't, because he's got this lab over he's in Italy actually. He's got this lab over in Italy. How am I getting over to Italy to go and use my algorithm in his lab? And so that's actually driven a lot of my research over the last couple of years, is how can I somehow provide some method for apples-to-apples comparison. And so I've asked a couple of different students to look at that particular problem, and we've come up with a couple of different solutions. One is, I want to share my lab. I can share the specs of my lab, but it still costs a couple of $100,000 for someone to buy it. So unless they have that money, they're not going to do it. And even when they do buy it, I notice Ray's SCADA lab doesn't look like my SCADA lab. It's going to be very similar, but he chose 2 different critical infrastructure. So we still don't have apples-to-apples comparison. But what if I virtualize my lab? And I'm going to show you that in a second. So we virtualized, or are in the process of virtualizing our SCADA lab. We've only got 1 of our 7 systems completely virtualized. And then the other thing is sharing data sets. And Actually, that one really excites the research community. We started actually just going into our lab and exercising the attacks with a data logger on, collecting all of that information and putting it into a multi-gigabyte file and sharing it out, and people really love that. In fact, I just presented that at a conference, and I was introduced as the guy that was solving all our problems, and that really made my head big. So the virtual labs, I'll show you in a second, but basically what we've created is a virtual client and server system. We have these systems have programmable logic controllers, so we virtualized both a programmable logic controller and virtualized the physical system, all in Python. And then we also have connected it up to a real-world human-machine interface as our server. And so what we get is a human-machine interface where you can actually interact with the physical process, although it's virtualized. We have real network traffic going back and forth that I can then use Wireshark or something like that to capture. And then I can also attack that system and look at the implications of that attack against the virtual process and capture all the data logs associated with the attack as well. So let me switch over to the virtual lab. This is the boring part. I want to show the boring part first. This is the server. So it's the slave system. It's just two terminals running there. I'm not going to show it to you again. But we have one virtual machine running here that's a server. It's also a simulation of a gas pipeline running in a second terminal. You'll note that the three virtual machines that I have, I've got the RTU and physical process on the far left. I've got an attacker. I'll show you that in a minute. And then I've got the MTU. I'm going to switch over to the MTU. Okay, so this is a human-machine interface screen. So these are actually pictures of 5 of the 7 labs that we have. The other 2 run in a different software system, but only the gas pipeline is implemented right now, so that's why it doesn't have a red X. You start at this screen, and then we'll click on it, and now we are connected right now to a gas pipeline, and a human-machine interface, by the way. So we've got an image of our gas pipeline. We've got a couple of meters here up at the top measuring pressure. One's analog, one's digital, but otherwise they're both just pressure meters measuring at the same point. And our gas pipeline also has down here in the bottom right-hand corner a solenoid that controls a relief valve to let air out. But what I can do, I can actually, and this is just exactly how a human operator would interface the system, reach over here, click it, I put it into auto mode, and now it's turned on. You can see the pressures going up. This one, the setting, I'm going to set it up to 20 psi because the simulation model that we have works better at 20 psi because it's a curve fit, and the curve fit was actually done at 20 psi. But so what is happening now, the system's just increasing pressure. It was off at 0, so it's going to increase up to 20, and when it gets there, that's what I was saying about, we need to switch to solenoid mode. Now it'll keep going up to 20. When it gets there, what it's going to start doing, it's harder to see, but it'll start opening and closing this red valve here to let air out whenever the pressure gets above 20. So this is essentially the lab that we have, except it's physical in the lab. So you can see it now. It's going to keep that pressure right around 20. Whoops, a couple of cool things that we can do. We can switch back over to the boring screen and we'll run Wireshark here, and we'll start up just so you can see that there is Modbus TCP traffic going back and forth. The virtual system actually supports Modbus TCP and Modbus over serial line. So here you can see Wireshark capturing these Modbus Ts. Those are Modbus TCP packets going across the line real time. So now with Wireshark, I can capture my data logs like I want. I can look down into the payload and see exactly what's happening with the system. And then next thing I can do is I've got one attack that I can run. All these passwords. And they're all password, by the way. We're actually developing this for a lab for students. We have 3 labs we're developing for a class. The first one's an introduction to control systems. The second one is this. We're going to introduce them to how to attack. And then the third one is how to do IDS on a control system. So if I go back real quick to the HMI, it's still sitting there at 20. I'm not interfacing. I'm not going to change anything. I'm going to go to my attack routine, and it looks like it's working. I've had some trouble with these virtual machines. But yeah, so now it's going to actually, it's doing what's called we call it a set point attack. It's sending invalid commands over to the MTU, and you can see the pressure's just starting to build up to 26, or beyond 26, and it's just going to keep going for a while. This attack just will ramp it up. But that's the virtual system. What that enables, as I mentioned, is other researchers that can't afford a lab. Now, what we're doing, we're going to put all of our attacks in here, and we're going to share that out so that other IDS researchers can also validate their IDS against my attacks. What I want is also, I'd like to have an open source paradigm where people start adding other systems. We've actually added we worked with the Army Corps of Engineers. You see, we're over 50 PSI now. We have a high pressure alarm, and it's just going up because the attacker is doing that. Anyway, we have worked with the Army Corps of Engineers. We built on this model a electric generation plant from a hydropower facility. So we actually went over to a hydropower dam in Georgia and worked with their engineers to virtualize their system. So I'm pretty proud of that, basically because so many people after I show it come up and ask me if they can have it. And the answer to that question is not quite yet. We have a license issue on that HMI screen. We're quickly porting it over to an open source HMI so that we can give it away. So I'll never be able to give that exact screen away, but we will be able to give a Linux-based open source HMI version away. And this was just to show you how the HMI, the gas pipeline works. So that is one of the things I do, and we're looking at, I want to virtualize an interstate gas pipeline, and so right now we have just one PLC and one master. I want 100 PLCs, and I want to do coordinated attacks across the system and capture data logs of that. So that's where we're going with that particular one. On the electric transmission side, Ray mentioned we've been working with PG&E and Entergy for quite a while. I think I started working with PG&E in 2009 and Entergy in 2011. So we have a very nice electric transmission lab. We have something called a real-time digital simulator that simulates high voltage lines and substations, breakers, etc. And then we have what's called a hardware in the loop configuration where we have real relays and other measurement devices that hook up to our RTDS simulator. And so those real hardware actually think they're monitoring and controlling a real system. So what do we do with that? One is just hardware in the loop simulation. I have a PhD student that really concentrates on implementing a lot of different types of control schemes so that before we can attack them, we have to actually have these control schemes. So right now we have distance protection and overcurrent protection with automatic reclosing. I know that doesn't mean much, but basically that's when your high voltage line has a short circuit, these two schemes protect the system by opening a breaker and turning off your lights. And then we've extended that, so besides having those control schemes implemented, we simulate power system disturbances, so actual short circuits and a bunch of other disturbances, and simulate cybersecurity attacks. And then what do we do with that? The same thing we did with the other. We collect data sets so that we can train and validate our intrusion detection systems. We've recently, the first time we did a data set, it was rather mundane. We just went into the lab and turned attack on, turned attack off, captured some normal data. It wasn't real random. There wasn't a lot of statistical variability. With this one, we actually implemented a random loop that calls all of our different scenarios at random so that we have both a random order of activities and random parameters from the attacks and actually random system state as well, so that we can introduce a lot more noise into our data set to make the IDS harder. This is just one of our power system models. I'll skip over it. It's a 2-generator, 2-bus system, but that's actually a very small system, but it's enough to do a lot of our research. And I already mentioned we script it up to be random. In this lab, I really think of it as sensor fusion. In the SCADA lab, we were only looking at just network packets. We're pulling out the payload, so we're doing some deep packet inspection. But in the electric transmission lab, we're grabbing information from many sources. So you see a lot of all these bubbles out to the side, and all the comma-separated list is all of the various parameters we're pulling in. And so what we're trying to do is take both network information, information from SNORT actually, and system information about the electric transmission system, and use all of that in a fused way to better understand what's the system doing, what's happening now, is it a disturbance, is it normal, or is it a cyber attack, and classifying that, each of those when they occur. So what have we done? We've done a lot of cybersecurity attacks in that lab, and then we've done a lot of disturbances and control actions. I don't think anyone is power system, so I'm not going to go deep into what those are. But we run, actually that slide looks fairly minimal, but there's 41 attacks and scenarios that come out of that, and then we run those at random with random parameters to test, or to build our data set. With our data set, we've done a couple different things. For anomaly detection, I'm actually collaborating with a guy named Justin Beaver and Raymond, two guys, Justin Beaver and Raymond Charles at Oak Ridge National Labs. And I send the data sets over to them, and they actually look at how can they detect, they're all marked with what attack actually occurred at any given time. And so they actually use machine learning algorithms to see, can a machine learning algorithm actually detect and classify these different attacks. And they've actually done a survey where they looked at a bunch of kind of off-the-shelf machine learning algorithms from a tool called Weka, and now they're moving into a specific anomaly detection engine that Justin Beaver has been developing for the last 5 or 10 years. And what they've found so far is these algorithms are not real good at detecting an individual attack and classifying it by name. We can group things and classify by normal or anomaly, but it's very difficult for these algorithms to actually know this is a denial of service attack, or that one's actually easy, but this is a command injection to open a relay versus a relay opening for a short circuit. It's very hard for these algorithms. And so what we've been doing in the lab is what we call causal events for IDS signatures. And this is a weird looking chart, but I've struggled for like 2 years to figure out how to show this, and I'm probably still not there. But this is 3 different scenarios that are occurring over time, and we have 5 different measurements down at the bottom. And what it shows is, if you follow a blue line, time's going up the y-axis. These things actually occur in something of an order. These are box charts, and so what they show is when this event happened over a range. It's sort of a histogram of when that event occurred, and you can see that the blue line is a fault at 30% of the line, and that that blue line has a signature. It's R2-1H, which is relay 2 high current, then the relay trips, then we see relay 1 trip after relay 2, and then we see R2's current go to 0, and then R1's current go to 0. And so that causal path there actually is a signature of that event. And so what we've been doing with our data set, we built up a huge data set. We ran those scenarios 10,000 times, and we have an automatic extraction engine that is pulling out these paths. And this graph on the right is even more hard to read, but that's actually 20 or 30 different paths for our 20 or 30 scenarios. We have 41, but I don't think that shows 41. I got that from a student. But what it shows is over time, the system is going through different states, and we automatically extracted these paths from, or signatures from a large data set, and then go back and validate with 20% of our data set. And what we're seeing right now is we have about 90% accuracy on classifying each individual scenario rather than just normal or anomalous. So what you can do is couple this with a normal or anomalous. Those are typically pretty good. But after you know something's anomalous, you can run the post-process through a system like this and actually know what actually occurred, so then someone can do something about it. If you don't know what it is, just anomalous, just wake somebody up in the middle of the night. If you wake up with an actual classification, then that person that wakes up can actually take action, and that's where we're trying to get. In addition to the intrusion detection work and the laboratory work, we've also done some cybersecurity testing and risk assessment. This is a project we did for PG&E and GE. GE sells some boxes called relays, phaser measurement units, and phaser data concentrators. And the PMU and the PDC, the last two I said, are actually pretty new. And when PG&E decided to put those in their system, they contracted with us, and the first thing we actually did was write cybersecurity requirements. The electric utilities right now, they're getting better, but they're not that good at cybersecurity. So they actually came to me just for the requirements. I had to go out and read a lot of document, standards online and build a set of requirements. GE insisted on, and I understand, requirements that actually traced back to standards. And so I wrote up requirements, and then once we had those in place, we went through 4 loops of testing the devices in our lab for conformance to the requirements and also just for looking for vulnerabilities. And each time we went through a loop, the devices, we'd send back a report, at first they were like 150-page reports, back to GE and PG&E, and they would apply fixes to firmware. We added a lot of architecture changes. Example of an architecture change is they used to have passwords on the boxes that were only numeric digits, and they were up to 9 digits long, so count up to 1 billion, I guess. And so that password was actually stored in the system. You could see it over Modbus. It was stored in an encrypted form. It turned out that encryption was just XORing the number with a fixed value. If you knew that fixed value, it was very easy to get back the password. Turns out if you put in the password, if you XOR a number with 0, you get that number. And so first thing we tried, well, let's put in the password of 0. It'll just give us the fixed key. That didn't work. But 1 billion fits actually in 32 bits. We just did 0 in 8 bits at a time, and we got 8 bits of the key. So it took us 4 settings of the password to learn that fixed key. It's the same key in every device they have at a certain firmware and below. But they replaced that with Radius at our recommendation, Radius authentication. And so, a lot of changes there, and the devices, I feel like, at least Northern California using these relays and PMUs is much safer from cyber attack than they were 2 years ago or 3 years ago. We did a lot of different testing looking for vulnerabilities, denial of service. Ray mentioned purchasing a fuzzer here. This is some work that a fuzzer did, just ramping up really high volumes of traffic. on lots of different network protocols to see what the devices do. These SCADA devices often just roll over. They don't have network stacks that can handle that kind of high volume traffic. For instance, InMap, if you InMap a SCADA device, a lot of them will just, they'll start into a reset loop, or they'll just, you'll kill a process and it'll just hang. Just finding those vulnerabilities and getting those closed down in the firmware was important. We did a lot of fuzzing. We had a fuzzer that was given to us, and I'm pretty proud of this. It was given to us, we were given a license, and then the company sold to another company, we lost the license, and the new company didn't want to give anything away to a university, so we wrote our own. It was a little bit of a panic because we had a report due. We would get these devices back every few months, and the students went off and in Python wrote 2 fuzzers in about 2 weeks. And the first fuzzer was what we did was just use a man in the middle. So normally this was for fuzzing a PMU to a PDC, 2 network devices. Normally you have traffic going from the PMU to PDC kind of constantly. We stuck a man in the middle in there to capture that traffic with we used EtherCap plus some Python to implement our man in the middle, and then we would get each packet a frame of IEEE C37.118 data, which that's a protocol specially for these devices. And we did 2 types of fuzzing. The first was dumb fuzzing. We just flip a random number of bits in that frame, recompute the CRC, and send it on. That by itself, just randomly flipping bits, killed the device a number of times, and we would document, what bit was flipped, and et cetera, and give that back to GE. And then we did something called smart fuzzing, and smart fuzzing is actually intelligently altering the packet. So for instance, you might have a packet that's 100 bytes long, but the length field, you might put it at 50. And that causes like a stack overflow and things like that. So we did that fuzzing. This is not cybersecurity, but it's a project with Entergy that we're actually doing something called relay settings automation. I'm really proud of it. The relays are actually the fuses in your house or the breakers in your house. Look at usually 15 amps. If the current goes above 15, they pop open. That's much more sophisticated in a electric transmission system, but basically it's the same idea. But each relay has custom settings. We're writing those settings automatically with a program now. What we found, we have 37 test cases from the utility. Every single test case, our program, when we ran it, gave a different result than a human did by hand, and nearly every single time there were some bugs in our program. But out of the 37, every single one of those cases, there was a result that a human created that was wrong compared to our computed value. Our computed value is based on their standard process for how to do it. So we implemented that, in an automated routine. So we're really proud of that. We're going to production with that at the end of this month. And actually, that's production inside Entergy. And now Aspen, a company that sells some software that we actually host in, or host our process, they offered 2 things. They first said, can I license it? I don't think they really want to. But what we're talking about now is launching a working group to standardize across industry. I don't think they'll want to license it yet because they haven't standardized across industry. It won't be valuable yet. Am I doing on time? I'm out? All right, well, one more thing, 2 minutes, I promise. We're doing something really cool with cybersecurity education. This is my last slide anyway. We've hooked up with the National Security Agency, and we have a set of problems at the beginning of the semester of a class. We're doing this with 4 universities, but we get a set of problems. The students get the problems from the NSA engineers. They review the problems, get online with the NSA engineers and ask questions about it. Then they write a proposal for a semester-long project to actually research in that area. And then throughout the semester, we have meetings with the NSA engineer. And basically, by the end of the semester, they've gone through the full hypothesis to validation research process and written a final report and given it over to NSA in conjunction or in whole time while communicating with the NSA engineer. So it's a great way for them to get noticed by NSA and for NSA to notice the research capabilities of the university. And I'll leave it at that. And thank you for having me. If anyone has any questions, please feel free.